All right, so today we have a guest lecture. This is my graduate student, Mr. Grant Leday. He's going to be talking to you guys about cascaded op-amp, or excuse me, cascaded op-amp circuits. I got cascodes on the class. If there's anybody in Zoom, please type something in the chat to let me know that you are here. The roll sheet is being floated about for people that are physically present.
All right, let's get started. So sometimes when we have op amps, one op amp isn't enough for us to have whatever our requirement is met. And so sometimes you'll see them strung together. And when you do that, it's called cascading op amps. And so we're going to work a problem with a cascaded op amp and find the gain of the entire op amp. And then I'll show you how to do it an easier way with a different problem. So let's write down our circuit. If y'all have questions, feel free to stop me.
Don't forget to turn the input of this one to the output of this one, not the output of this one.
Oh yeah, here, right here.
So, thank you. Yeah, sorry, I noticed that error.
All right. So sorry for the awful handwriting, but this is the first time I've used this tablet, so just bear with me on that. Also, the little thing like this is ground. Pretty sure Dr. Hartman uses something else. So that's ground. So yeah, so what we want to do is find an equation, V out equals the gain times V in. And so we're going to solve this for A, okay? Whenever you do op amps, you have to make sure you remember your two rules. You can't have current flowing into the input, right? So no current flows in. And you also have to remember that the voltages at the legs, each input terminal, they have to be the same. Voltage at input terminal. All right, so there are some tricks to solving these a little easier. Yeah, I think so. That's not a good place to have that.
Yeah, no. All right. So chill out for like literally 5 minutes.
Okay.
I had a student 3D print this one because I kept hitting that one with my knee. Yeah, but there was a cover on this one, but somebody else, not me, broke that one off. So I'll have to have somebody else 3D print the thing. There's two switches on the big power supply on the front of this thing that are right at knee level. So if you move too fast, you can literally shut the entire system down. So,
Sweet. All right.
So 5 minutes impromptu, ask Grant anything.
Yeah. So I just graduated last year in electrical, so fresh out of my bachelor's. So if y'all have any questions about that, I'm assuming y'all are all electrical, right? Or some biomed. Right? Oh, I'm electrical. Okay. Sorry. So we got one electrical. So what y'all got? Anything? No, Mason, you Did you graduate?
No, he's graduating this year. He is a cross-country runner or something like that as well. Yeah.
Is he the one with the beard? Yeah. Yeah. Nice. Cool. Yeah. The third year.
The junior year is the most butt-kicking of years for sure.
Yeah. Yeah, I would say the fourth year is easy enough. What did you do for your senior stock? So I did a platform that posed CubeSats. So CubeSats are like little tiny satellites that universities a lot of times will put up in space to run like a single experiment. So I did something that like posted a bunch of them. Y'all have any ideas about senior design projects? Floating around? What do you want to do when you graduate? Get a job? Yeah, I want to teach. So if this goes well. Yeah.
No pressure.
Yeah. That's a good question.
Last year there were 11 senior design groups. That means it was somewhere, yeah, low 40s, I think. This year it's going to be, I think 38. Next year it's going to be really close to 60, actually.
Maybe.
Well, if I can get them out of analog electronics, it'll be close to 60. We shall see.
How's are y'all in analog electronics? No, that's not them.
That's 335 and 336. Yeah. So.
What's the hardest class? Undergrad. Mathematical methods. Physics 4 and I like control theory and electromagnetics, kind of both fields. Y'all get into that next year, I guess. Electromagnetics is a lot of like physics stuff. Right, I was a physics major for a while, so I guess that's why I like that. A lot of physics and Cal 4, so hope you
Yeah,
do well on Cal 4.
vector calculus is all what you're going to do in your 313 and 411 class. Just oodles and oodles of vector calculus.
Yeah, they really just teach that just for y'all.
Pretty much, yeah.
Go ahead. What calculus are y'all in? Kind of roundabout right now. 52? Okay, so y'all take it.
Why is this not working?
Yeah, so I guess Fields is gonna be booty as well. What else I got?
What kind of dumb stuff have you done with electricity?
So you have to make a power supply. I guess next year.
Next fall. Yep.
Next fall, yeah. And I blew mine up, but not. I was trying to do something. I ran it a little too hard and it blew up. But when we were actually testing them today, someone blew up theirs like on test day. So that was pretty fun. Yeah, I don't know. I think I'm pretty safe about it, I guess. If you understand it, hopefully it comes a little easier. But, yeah. Anything else?
All right, it's close. Now we just have to wait. The system was on the entire time. Press one button and you can get back in.
Y'all thought y'all were going to learn today.
And all of this has been recorded on Zoom.
Sweet.
All right.
Any last questions before we start doing a lot of algebra? The problems are going to get easier, so this one's going to be a little hard and long. So don't zone out on this one, and we'll do a little easier one next.
All right. Be very careful with your knees.
Okay.
You're ready to go.
Let's see how many times I can kick it off. All right, so we were here. If you can't read my handwriting, this is RFA for your first feedback resistor, RFB for your second feedback resistor, R1 and R2 on the right side, and then we have RN right here. We have RAB between the first and second op amp, V out and V in. So, and RF at the bottom. All right, so going back to the tricks to help you solve these a little easier. Normally you want to start at V out. You want to start at the end and work your way backwards. Okay, so tricks. Start at V in or V out, sorry, and work backwards. All right, and the second trick is normally nodal analysis will be your friend in these. It's kind of hard to use mesh or KVL, I guess. KVL, kind of be hard. So normally you want to do this all in terms of currents. Not that that will be the only thing that you ever do, but typically try that first and it'll help. So.
There is no relationship that is given with regard to tied to the input. The input voltages have almost nothing to do with the current that comes out, and that would be a required quantity to be able to do that. That's why nodal is the way it is, because the output voltage relationship and the input voltage relationship are well established.
So for y'all on Zoom, Dr. Hartman just said nodal works better because you don't know the quantity of current coming out of the op amp. And so it's hard to write KVL equations with the current. So typically you want to do nodal equations, which use the voltages, which are known quantities most of the time. All right, everybody got the circuit down? Everybody good? Cool, so let's start. So like I said, you want to start with V out. And so we're going to start writing nodal equations for V out. I'm going to turn this to red. So I'm going to start defining currents all over our circuit. So let's call this current I2. Let's call this current I1. And let's start here. Okay, so if we write an equation for I2, we'll have I2 equals, I guess we have to define a voltage as well. Let's call this voltage VA, this one VX, call this one VB, we'll call this one VY. Now, you see that VY is connected to the non-inverting terminal right here of this third op amp. And so VY is VY all over this node. And also we have our rule that the voltages have to be the same across the terminals. And so VY is also right here. This voltage is 0 because it's grounded. This voltage is 0 because it's grounded. What else do we have? We have IA, we'll call that IA, so the current through that feedback resistor. We'll call this current IB, call this one IAB, and then we'll call this one IN. I know that's a lot all at once, but it's just going to make it easier down the line that we have everything defined and know what we're looking for. If you notice, I tried to keep the naming convention easy enough to understand. VA, VB on the inputs, VX, VY on the outputs. And so let's go from here. So I2. Oh, yeah, that's IF. Would have realized eventually. All right, so we have IF. All right, so I2, the relationship here is VY minus V out over R2, right? Easy enough. VY minus V out over R2. I guess it's important to know what we're trying to do also. So right now we're trying to write an equation for V out in terms of VY, the input voltage, okay? So we're going to write a small gain equation for V out, but we're going to do that using the currents. We also have I1 equals VY over R1. So this should be pretty easy so far. Now we use that rule from the beginning that we can't have current flowing into the input terminal, right? And so the current can't be in this leg right here. It has to go from here to here. And so I1 and I2 have to be the same except for a sign, right? They're facing different directions, so they have to have a different sign. But they're the same magnitude. And so we can say negative I1 equals I2. And since we have equations for both I1 and I2, we can plug them in. And we'll have negative VY over R1 equals VY minus V out over R2. And so, like I said, we want an equation for V out in terms of VY. And so we want to group all of our VY terms on one side, our V out term on the other side. And so we get V out over R2, like a negative, equals negative VY over R1 minus VY over R2. Okay, so I just split up that fraction on the right. And now we're going to factor out a VY from the right side, and we're also multiplying by negative R2. And so we get V out equals negative R2 VY 1 over R1, negative 1 over R1 minus 1 over R2. And so if we multiply through by R2, we get V out equals 1 plus R2 over R1 times Vy. Everybody okay with that? Now, this is what you would expect. We had a non-inverting amplifier right there, and this is the gain equation for that. And so that checks out. And so now that we have this, well, we need to know what Vy is. And so we keep working backwards. So we go back up to our circuit right here, and we start writing equations to solve for Vy. And so we want the equation for IB. So IB, oh, that's an I, equals, and then this is VB minus Vy all over RFB, right? Now, remember that the, that's a B. Ooh. Oh, we're going towards right here. This is the,
Or maybe not, okay. That one with the red thing.
gotcha. All right, so going back up to our circuit, we have this leg right here of our op amp grounded, right? And so since the voltages have to be the same at each leg, that means that VB has to be 0. And so that kind of simplifies this equation a little bit. So we can say this is 0. And so all of this equals negative Vy over RFB. Now this would typically be it, but we have another branch, right? And it's this branch right here. And it has a current IF. And so let's write the equation for IF. IF equals VB minus V out over RF. And again, VB is still 0. And so we get negative V out over RF as our IF. And so last thing we need to do is write an equation for IAB, which is the current between the two op amps. And so that'll be Vx minus VB over RAB. So IAB equals Vx minus VB over RAB. And again, VB is 0, and so we get Vx over RAB. Now, going back up here, since the current cannot enter our op amp from the input terminal, IAB has to split at this junction and go up and down, right? And so we can write the equation IAB equals IB plus IF. They have to be equal. Now, we have equations for IB, IF, and IAB, and so we're just going to plug all of this in and solve for Vx, Vy. So IAB is Vx over RAB. IB is negative V Y over RFB. And then IF is negative V out over RF. Okay? So again, yep. So again, we're trying to solve an equation for Vy in terms of Vx. Now I know there's a V out in there, and we're just going to leave it because we already have an equation for V out. And so let's just try to get Vy on one side, Vx on the other, and solve it that way. And so we'll have negative V, kind of cutting into this one, negative Vy over RFB equals Vx over RAB plus V out over RF. So solving for Vy, we'll get Vy equals negative RFB times Vx over RAB plus V out, that's an X, V out over RF X up. So now we have our Vy equation. I'm gonna put a little line under that one to know that we're here. And we have our V out equation right here. And so we have one more to do, and that is our Vx equation. So going back up to our circuit, let's look at this. So we have IA flowing through that feedback resistor, and we have IN flowing through our input resistor. And so we'll put IA equals, and then that would be VA minus VX over RFA, right? Voltages on either side divided by the resistance. VA minus VX over RFA. Now, VA is 0. Same reason that VB was 0. It's grounded right here, which means VA has to be 0. So we'll put the 0 right there. And we get IA equals negative VX over RFA. Okay? And so the last equation we need right here is for IN. And so we can write IN equals VN minus VA all over RN. Oop, down. And again, VA is 0, and so we get IN equals VN over RN. Okay, so right here, again, we can't have current flowing this way. That's a big no. And so IN has to go up and flow through our feedback resistor, right? And so we can say that IA equals IN. So let's make this. And so we have equations again for IA and IN, and so we just plug them in. VX over RFA equals VN over RN. And we're looking for an equation for Vx, and so we can just multiply by negative RFA. So Vx equals negative RFA times Vn over Rn, which you might recognize as the inverting gain formula because we had an inverting op amp. So again, checks out. And so we have Vx, we have Vy, and we have V out equations. And so we can just start plugging everything back in to the bottom. Any questions before I start doing that? Cool. And so Vy equals negative RFB times Vx over RAB. And so we have Vx, right? Vx is right here. And so we'll plug that in, negative RFA over Rn Vn all over RAB plus V out over RF. And so we can simplify this down just a little bit, and we'll get RFA, RFB over RAB, Rn times Vn minus RFB over RF V out. Okay, all I did was multiply out that negative RFB, and then RAB, I just multiplied by the reciprocal, right? And so that goes into the denominator. All right, so let's move on. So we have now an equation for Vy in terms of Vn, and so we're going to plug all of this back into our V out equation. And so V out is this equation right here. And so we have V out equals 1 plus R2 over R1 times all of this stuff, RFA, RFB over RAB, RN, VN, minus RFB over RF, V out, like so. And now we have an equation for V out, but we also have V out in the equation, right? And the whole goal is to get V out on one side and V in on the other side and some term between them. So we want something that looks like V out equals A V in. And so to do that, we're gonna have to multiply through, FOIL these terms together, and then we're gonna have to group like terms on one side, group like terms on the other side, and do some dividing. Okay, so I'm gonna rewrite this equation on this page. So we have V out equals 1 plus R2 over R1 times RFA, RFB over RAB, RN, VN minus RFB over RF, V out. Yep. So let's FOIL it, and we get V out equals RFA, RFB all over RAB, RN, VN minus RFB over RF, V out plus RFA, RFB, R2 over RAB, RN, R1, VN minus RFB, R2 over R1, RF, V out. And so we're going to group all of our V out terms on the left side, all of our V in terms on the right side, and we'll get V out plus RFB over RF, V out plus RFB, R2 over R1, RF, V out equals RFA, RFB over RAB, RN, VN plus RFA, RFB, R2 over RAB, RN, R1, VN. Okay, almost here, home stretch. So we have a common term of V out on our left side, right? So we're going to factor out a V out of all those terms. Same thing on the right side, we have a common term of V in, and so we'll factor out a V in. And so we'll get V out times 1 plus RFB over RF plus RFB R2 over R1 RF equals, and then RFA, RFB, RAB, RFA, RFB, R2 over RAB, RN, R1, BN. Okay. All right, so now we're going to divide by this term on both sides, all right, to get rid of it. So we just have V out on the left. And so we end up with V out equals, and then RFA, RFB over RAB, RN plus RFA, RFB, R2 over RAB, RN, R1, all over 1 plus. And we did it. We found A, right? So this whole huge thing is A. And so that's the gain of our circuit. So now if we had all of those values, so those are all resistor values, right? And so we would have those in a real circuit. We could plug in all of those numbers, and then whenever we plug in a V in, we know what V out would be. And so we don't really have to solve this again. We don't have to solve this whole circuit again every time we plug in a different input voltage. If we know our resistor values, we can just plug in V in and all our resistor values and get V out. Yeah, that's cascaded op amps the hard way. The hard way. Anything you would like to input before I move on?
Yeah, just really the reason why this particular example is so difficult and it's so mathematically rigorous is because there was a feedback path.
Yeah, so that's a.
It does happen. But generally, this class, you could expect things to more.
Yeah, so this is a bad loop right here because it's connecting two of those op amps together, output to input, and so it just makes it a lot harder. So I'm going to do another one without that loop. A pretty similar problem. The first amp is a little different, but yeah, I'll show you that one and show you how much easier it is to solve. All right, let's dive in. Oops, still red. That. So again, we're gonna have 3 op amps in this one, cascaded together. So we'll have a resistor here, the voltage source, plus minus 1, a resistor here with another voltage source, Okay, so this is our next one. Notice that there's no feedback loops stretching across multiple op amps, like front to back. So yeah, we're gonna solve this one the hard way real quick. Is that okay? So yeah, we're gonna solve it the hard way, and then we'll solve it the easy way, show you how much easier it is to do the easy way. So again, we're gonna start just like we started the last one, identifying a bunch of stuff, and starting at V out and working our way backwards until we get to V in. I'll get ready soon. Okay. So we'll call this node VA, this one VB, oh, not VB, VX. Call this one VB and this one VY. And then again, note that this is also VY over here, and so is this terminal, because they are input terminals of the op amp. And then let's label some currents, and so we'll have I2 again, I1 again, IB, IA, IAB, and I'm just going to call this one IC. Okay. So we're going to do this, and it looks very similar to the last one, a little different, but it is a lot easier because they don't have that feedback loop, and so the equations will come a lot quicker. And so we'll have, starting at our last terminal, I2 equals VY minus V out over R2. All right, so that's just can it. Right, so up until now, you've been studying passive devices, right? And so that's devices that only have power when you power them, right? They don't generate their own power. Op amps are not passive. So you actually have to supply a voltage. So typically, an op amp will have more rails. You'll have the output, the two inputs, and then you have these rails right here. Right, right. And so you're not actually following the current all the way through, per se, because it can generate its own current. It can use those voltages to output whatever current it needs to.
Can I addendum to exactly what you're talking about here?
Sure.
So what the suggestion is, or the question from the student was, if we observe the current flowing in the sky, I'm going to do it in purple here, right? So we have our input signals all generating some current, and it happens to come out to be IC. We're going to see that current IC flow through this feedback resistor, flow through that resistor RAB, flow through this feedback resistor, and then we get to this point in the circuit where things start to look a little wonky, right? So I'm going to put a question mark here. We know that this current has to be 0 amps. So what that means is that our purple current is actually flowing into the output terminal of our op amp, because we don't have any restriction on the amount of current that can flow into or out of the output terminals of the op amp, only the input terminals, right? So what Grant was suggesting, what's actually happening is it flows into the output terminal, and its path to ground is through one of the power supply connections, physically inside the op amp. So it looks like, at first glance, I absolutely understand why you would say all of this current has to be equal to 0, but we can allow current to flow into or out of the output terminals of that op amp. So unfortunately, it's not as easy as saying all those first stages don't actually do anything and going from there. So let me erase this and then let Grant get back to doing what he's doing. But that's a fantastic question. Sorry.
Are you?
Thing. So yeah, back to I2. Any other questions before we kind of dive into this one, I guess? All right, get ready for some algebra. Oh, that's still orange. All right, so we're gonna write our equation for I1 as well. And so I1 is simply Vy over R1. Now, just like the last circuit, you can't have current flowing into your input. That's a big no. And so I1 has to be the current flowing through the resistor 2 as well. But again, we just define them in opposite directions, right? So if you kind of follow this line, I1's going down and I2 is going this way. And so they're just opposites of each other. And we'll say negative I1 equals I2. And then just substituting in our equations, we get negative Vy over R1 equals Vy minus V out over R2. And we want to solve for Vy, or V out, sorry. And so we'll get negative Vy over R1 minus Vy over R2 equals negative V out over R2. This will give us V out equals R2 Vy over R2 plus Vy over R1. And I know I just switched around all of the variables, but this will make it look more like it is in your book. So if we factor out a Vy and also multiply it through by R2, we'll get V out equals Vy times R2 over R2, which is 1, plus R2 over R1. And again, this is the same equation we had last time because this is a non-inverting amplifier setup. And so this will be the gain equation for that. All right, so going back up, now we need an equation for Vy, right? And so let's start writing nodal equations here. We have VB minus Vy over RFB equals IB. Right. But since we have our terminal grounded right here, that means VB also has to equal 0. And so that kind of simplifies our equation a little bit. And we get IB equals negative Vy over RFB. Cool. And so we also have IAB right there. And so IAB, we can write an equation for Vx minus VB over RAB. And again, VB is 0, okay? So that simplifies it a little bit. We get Vx over RAB. And so we can write one more equation relating IAB and IB, right? And we can't have current flowing into our input, right? So that's, again, 0 amps. And so IAB, when it reaches this junction, has to go up and flow through our feedback. Make sense? And so IAB and IB have to be the same current. And so we can say they're equal. Now we can just plug in our stuff like we've been doing, and we'll get negative Vy over RFB equals Vx over RAB. solving for Vy, we get Vy equals negative RFB over RAB Vx. So that is our Vy equation. And then we need one more equation for Vx. And so we start with the equation for IA, and IA is just VA minus Vx over RFA. VA is 0 volts, right? Because again, we have that terminal grounded. So just like the last one, we'll get 0 volts for this. And so IA is negative Vx over RFA. Now IC is a little trickier because we have all of these voltage sources feeding into it. And so you'll have a current from this one, a current from this one, and a current from this one contributing. But we can see that they all add, right? And since VA is 0, we have IC equals to this first current, which is just V1 over R plus V2 over R plus V3 over R. So I see some perplexed looks. This voltage right here is 0 volts, right? And so if we want to find this current, it would just be V1 over R, right? Same thing here. This one's just V2 over R, and this current is V3 over R. And all of those will add together and equal IC. Okay. All right, so now we need to write an equation relating IC and IA. And again, they have to be equal because IC can't flow into the input terminal, and so it has to go upstream and go through this feedback resistor, meaning that IC equals IA. And so let's substitute in our equations, and so we get negative Vx over RFA equals V1 over R plus V2 over R plus V3 over R. Now, I chose R to be the same for all of these because that's typical for what's called a summer, but they don't have to be the same. So you could write equations for different R values. Anyway, we want to solve for Vx, and so we'll have Vx equals negative RFA over R. So I'm going to factor out an R times V1 plus V2 plus V3. Okay, and then substituting all the way back in, we can say Vy equals negative RFB over RAB times negative RFA over R times V1 plus V2 plus V3, and then V out equals, I'll write this one first, 1 plus R2 over R1 times Vy, right? And Vy we just wrote down, and so we can just say it's times RFB over RAB. One plus R2 over R1 negative RFB over RAB, and then times, not that one, negative RFA over R times V1 plus V2 plus V3. And so again, we've written our output in terms of our input. So V1, V2, and V3 are our input voltages, and it's all multiplied by this. And so this becomes our gain, our A. Now that was hard and long, and so let's do it the easier way without so much algebra. So going back up to our circuit, let's start identifying things. I'm gonna do this in purple. Purple. So this circuit right here, does anybody recognize this one? Yeah. So Dr. Hartman just said, ignore everything to the right of the purple. Just the stuff inside the purple. What circuit is this? Summer, right. So it's a summing amplifier. Now, if you flip to whatever page it is, it's 182 in the, okay. Well,
What we talked about last time. Inverted summer, the gain is the negative or
yeah, so what Dr. Hartman is saying is that the gain for an inverting summer is the feedback resistor divided by the input resistor, and it's negative, all just times the sum of all the voltages for the input. And so if we go back and look at our circuit, our input voltages are V1, V2, and V3. Our input resistor is R, and our feedback resistor is RFA, so this one right here. And so we can plug all of this in for our circuit, and we get A equals, oh, not this, yeah. Actually gonna be V out. V out is this. So yeah, in our case, Vx will equal negative RFA over R V1 plus V2 plus V3. And let's just call this our input voltage, Vn, and this our output, Vx. And so we have our gain right here as A1 equals negative RFA over R. Now going back up to our circuit, maybe not. There we go. Do this one in blue. So let's look at this circuit right here. Does anybody recognize this one?
some voltage to that resistance, that and on that resistance RAV. So everything to the left of that blue circle should be replaced with a voltage source.
Negative feedback, right? And so it's, right.
Specifically, this one is 100. So the input is applied through that resistor to the inverting input. So that makes this.
All right, so this is, right, this is an inverting op amp. And so we know the gain equations for this one as well. So going all the way down for inverting op amp. Our gain equation is going to be very similar to the one right above it. And we have A equals negative R feedback over R input. And so we can write V out equals negative R feedback over R in times V in. Okay? And so we'll call this gain 2. We'll come back to it. So last one, do it in green. So again, we're just considering the op amp that's inside of the green circle now. And everything to the left of it is just a voltage, okay? Just an input voltage. And so it would look something like, Right, okay, so this is a non-inverting op amp, non-inverting. And so we also know the gain equation for this, so non-inverting we have A equals, and then a positive RF over Rn. Oh, that's not it. Plus 1, but I wrote it as 1 plus RF, I think. All right, something like this, right? And so we can say V out, in this case, of just our non-inverting op amp, would be 1 plus RF over Rn, V input. Okay, so let's see how we can use this. Well, if we're trying to find V out all the way over here, well, we can say it's whatever Vy is for our input, and so V out equals 1 plus our feedback resistor, which is Rf, I believe. Nope, R2. Everybody cool with that? So the equation that we wrote with a bunch of algebra, we could just say it's this, right? And then Vy we can solve for. Vy, Vy is the output of our inverting op amp, this one. And so our input voltage here would be Vx, and our output voltage is Vy. And we have the gain of an inverting op amp. And so Vy equals negative RFB over RAB Vx, right? Because RFB is our feedback resistor, RAB is our input resistor. And so we need one more for Vx, and that is the output of our summing amplifier, the input being V1, V2, and V3. And so we can write our gain equation for that. So Vx equals RFA, so negative RFA, over R V1 plus V2 plus V3. And so we arrived at the same point we did earlier. We can just plug all of these back in and say V out equals 1 plus R2 over R1 times negative RFA. Oops, that should be a B. Oops. RFB over RAB times negative RFA over R times V1 plus V2 plus V3. And note, that's the same equation we had here, right? Exactly the same. And all of these just happen to be A1, A2. Oh, I have these backwards. A3, A2, and A1. So instead of doing any of this math, we could have just said that the output is the gains multiplied together of each of the stages of our cascaded op amp. And so it becomes a lot simpler than doing a bunch of nodal analysis. So V out equals A3 times A2 times A1, V in, V out equals A, V in, cool. Lose anybody? Did I not lose anybody? Right, cool. Yeah. All right, any questions before I guess we head out? Looks like Dr. Hartman's coming to talk to y'all.
So the importance of this is we can simplify the circuit analysis significantly if we can identify the stages of amplification that are happening, right? That's why we went through those common op-amp, or specifically negative feedback op-amp topologies in the last class, right? If we can't identify the different stages, we have to go through the brute force method that is as ugly as the first two ways that we, the first two examples that we looked at. If we can easily identify the stages and say, all right, so this is just an inverting op amp chained into a non-inverting op amp chained into a summer or a differentiator or an integrator or whatever, it becomes trivial because we know what all of those one stage to the next stage input output relationships are, and then we can literally just multiply things together. So cascaded op amps can be as difficult or as easy as you want to make them, depending on whether or not you want to take the time to learn what the different stages and all that kind of stuff look like. That's that.
The reason that they're cascaded so often, they're called operational amplifiers, and it's because they were used in analog computers to do just that, operations. So stuff like adding, subtracting, dividing, multiplying, integrating, differentiating. You can do all of these things with op amps just from inputs and outputs and making them look like circuits that we know. And so if you have a big analog computer like this using op amps, it'd be absolutely awful to go from front to back figuring out all the equations, where you can just multiply all of these things together and have it do what you want it to do. You know, actually use it to be useful.
So just look at the, so scroll up, right? Slightly too far. Okay. So let me borrow a pen.
Yeah.
And let's change the color to this guy, all right? All right, so this is the input stage, or this is where the input signal is applied, and this node right here between the two op amps is the output of stage one and the input of stage two. Similarly, this node right here is the output of stage two and the input of stage three. So you're just looking at those points of connections where the two op-amp circuits are connected to each other to give you the line where you look to the left of it to see how it behaves, and you look to the right of it to see how it behaves. That's how I would approach breaking down the stages. So again, ignoring everything to the right of the green line, that is obviously an inverting summer because there are multiple input signals being applied to the inverting input terminal, right? And they all have talk. That's why it's not a weighted inverting summer. For the middle stage, I have some input signal being applied at the inverting terminal, so it is an inverting amplifier. For the third stage, my input signal, whatever it is applied to the non-inverting terminal, so it's a non-inverting amplifier. That's it.
It also helps to know what they look like individually if you want to study.
So because there's a feedback chain from the input of op-amp 2 to the output of op-amp 3, we have to look at those two together. But we could eliminate a whole bunch of math by saying everything to the left of that green line is just a simple inverting op-amp. So we could have eliminated roughly a third of the work by recognizing the way that that portion behaves and just focus on the algebra for the two stages that are chained together by that one overarching feedback. So we could have still eliminated a fairly significant amount of work by identifying that. All right, anybody got any other questions or anything? All right, so on Friday, we are going to entirely switch gears and we are going to start looking at the transient analysis of second order circuits. So we're going to be looking, instead of RL circuits or RC circuits, we're going to be looking at what happens in RLC circuits, so circuits with two energy storage elements. So get ready for some calculus. So today was algebra, algebra, algebra. Friday will be calculus, calculus, calculus. All right, thank you guys.